In this lesson, we are going back to right triangles, and specifically, we are going to examine how right triangles can be similar using angle-angle similarity. We are going to be looking at how we can use the altitude and what's called the geometric mean to find missing side lengths and solve problems. So first we're going to take a look at the altitudes of triangles. In any triangle, doesn't matter what its shape is, there are three altitudes in any triangle. And the altitude is a segment extending from the vertex to the base of a triangle, and it's perpendicular to the base. So for example, in this red right triangle, I'm looking at this vertex, and I can draw an altitude all the way down the leg because it forms a right angle with the other leg. So this would be one altitude of this right triangle, and of course there are two more from the other vertices in this triangle. In the lime green obtuse triangle, this altitude is going to lie outside of the triangle. So from the tallest point down to the base, we are forming a right angle, and it is outside the triangle. In this equilateral triangle here, from the top of the triangle to the vertex of this triangle, we can draw the altitude as straight of a line as possible down to the base, and it forms a right angle. But we can also draw altitudes from the other angles. It doesn't necessarily have to be the quote-unquote tallest point of the triangle. We could draw an altitude from this vertex. As long as it extends from the vertex to the opposite side and forms a right angle. So that's what we're going to be doing today with right triangles. In the bottom right, you see this blue right triangle. We're going to be working with the altitude that's drawn from the right angle. So from this angle, I can draw an altitude, and it's going to form a right angle here. This specific altitude actually gives us some pretty interesting relationships in right triangles. So we're going to talk about angle-angle similarity. When an altitude is drawn through the right angle of a triangle, there are three right triangles formed. Three right triangles are formed. So you have the bigger triangle, ABC, and then when you split up the triangle along this altitude, you get two smaller triangles. You get triangle ABD and ADC. And they are all right triangles because altitude AD made them that way. So what I'm going to do to examine the similarity of these triangles is I'm going to redraw them so that they're all facing the same way. They all have the same position, like this. So for the sake of labeling here, I'm going to call the biggest triangle triangle 1. And then the second biggest triangle is triangle 2. And the smallest is triangle 3. And I'm going to go through really quick, and I'm going to label all of these points and the right angles. So in triangle 1, angle A is my right angle, and then this is C and B. And then in my second biggest triangle, I have DBA. And my third is DAC. Okay, so I'm seeing a few similarities here. I know that angle A in triangle 1 is a right angle, and I know that angle D in both of the smaller triangles is a right angle. So already all of these triangles have one pair of corresponding congruent angles. But let's look at the relationship between triangle 1 and triangle 2, the bigger triangles. I'm noticing that angle B is shared among these triangles. If I look back to my previous diagram, I can see that angle B it's shared, so it's overlapping. They're the exact same angle, so angle B is congruent to angle B. When I look at the relationship between triangles 1 and 3, the biggest triangle and the smallest triangle, I'm noticing that they're sharing angle C. Angle C is the exact same angle. It's shared. So we can write some similarity statements here. So my first one would be the relationship between triangle 1 and triangle 2. I know that triangle ABC is similar to triangle 2, which I'm going to call DBA, so that it's in the same order as a triangle ABC. So this would be DBA, from the right angle to the left and up to the top angle. So these triangles are similar because all right angles are congruent. So angle A is congruent to angle D. And they share angle B. So by the reflexive property, angle B is congruent to angle B. I also know that triangles 1 and 3 are similar. So triangle ABC is also similar to triangle DDAC, same order, because angle A is congruent to angle D, right angle theorem, all right angles are congruent, and by the reflexive property, angle C is congruent to angle C. The shared angles are congruent to each other. So now what I'm noticing, since triangle 1 and triangle 2 are similar to each other, and triangle 1 and triangle 3 are similar to each other, that means that triangles 2 and 3 are also similar to each other. So here's what that looks like. This is the transitive property, by the way. Since both smaller triangles are similar to triangle ABC, they are similar to each other. So I'm just going to reiterate that whole concept. This is true in any right triangle. So when you draw the altitude from the right angle, or the altitude of the hypotenuse of any right triangle, it's going to divide the triangle into two triangles that are similar to the original triangle and to each other. So if CD is the altitude, that means that all three triangles formed are similar. So if we are given this problem, we are given that triangle PQR is similar to triangle QSR, we need to find the length of QS. So we're trying to find the length of the altitude of this triangle. So what we can do is we can set up ratios of the side lengths, since we already proved that all of these triangles are similar. We can set up ratios, and then we can solve proportions to find the missing sides. So when in doubt, draw your triangles. So here's my biggest triangle, triangle PQR. And I am rotating this in my head and trying to make sense of this here. I know that the right angle in this triangle is angle Q, and then I have R and P. And so here's the information I know in this bigger triangle. I know that my short leg is 15, and when I draw the altitude of this triangle, here's S. I know that the shorter portion of the hypotenuse is 9 units, and I know that the long leg, PQ, is 20 units. Let's draw the second smallest triangle. So this is going to be, let me shade just so you know what I'm doing, triangle PQS. I know that the right angle in this triangle is angle S. And that means that I have Q here and P here. I know that the hypotenuse of this triangle is 20 units, but I don't know anything else. That's all I know in the middle triangle. And then in the smallest triangle, I know that my right angle is also angle S, and then here's Q and R. So I actually know quite a bit about this triangle. I know that the short leg, RS, is 9 units, and I know that the hypotenuse, QR, is 15 units. So our goal is to find QS. So that's the long leg in my small triangle, and it's the short leg in my middle triangle. So I don't really need to work with the biggest triangle. I'm going to focus on the two smaller triangles here. And I think since I am missing the short leg in my yellow triangle, and I have the short leg in my smallest triangle, I'm going to set up a proportion with those lengths. So in the yellow triangle, the ratio of the short leg to the hypotenuse is going to be equal to the ratio of the short leg to the hypotenuse in my smallest triangle. So let's fill in what we know. My short leg, I don't know it. It's going to be X. And my hypotenuse is 20 units. And that's going to be equal to the short leg in my blue triangle, which is 9, over the hypotenuse, which is 15. So from here, we've got an easily solvable proportion. We're going to cross multiply. X times 15 is just 15x. And 9 times 20 is 180. And when we divide both sides by 15, we get x is equal to 12, which means QS is equal to 12. So what we did, or what we're getting to in this lesson, is a concept called the geometric mean. So let's say we've got different numbers here. A and B are going to be my numbers, and X is going to be the geometric mean. So I can set up a proportion to find the geometric mean, which is X. So A over X is equal to X over B. All of these numbers are going to turn out positive. So to find X, to find that geometric mean, I know that I need to cross multiply. So X times X is X squared, and A times B is just AB. And so to find X, to find that geometric mean, I need to take the square root of both sides. So X is going to be equal to the square root of A times B. In other words, it's the square root of the product of two numbers. Pretty interesting. I know that you're probably used to, when you hear the word mean, you're probably used to what we call the arithmetic mean. The arithmetic mean, where we take two numbers and we find the average, meaning we add them together and divide by the quantity of numbers. The geometric mean, like you just saw, is the product, or the square root of the product of two numbers. Square root of the product. So let's try out this concept with tangible numbers here. We are going to find the geometric mean of 9 and 4. So I'm going to set up, for clarity's sake, I'm going to set up our ratio where the geometric mean is a cross product in this proportion. You're going to be multiplying the geometric mean, or x, by itself. And a and b are your positive numbers. So a and b are 9 and 4. I'm going to set this up. So a is, let's call that 9. It doesn't really matter the order anyway because you're multiplying here. So 9 over x is equal to x over 4. This will only work if your x is across from itself. So you're going to be multiplying x by itself always to find the geometric mean. So now I'm going to cross multiply, and I get x squared is equal to 9 times 4, which is 36. And so the square root of 36, the positive square root, is 6. The geometric mean of 9 and 4 is 6. So we're going to use that concept in triangles to find missing side lengths. The first corollary, or follow-up to the theorem we examined about the altitude in right triangles, is the length of the altitude going from the right triangle, or from the right angle. So that in this diagram it's CD. This altitude is the geometric mean of both parts of the hypotenuse. So CD is the geometric mean of AD and DB. And you'll notice we set up a proportion that way. Notice that CD, the altitude, is going to be the cross, you're going to take the cross product of CD. And AD and DB are opposite from each other as well. So let's apply that to this triangle. Given triangle RST, we need to find the length of UT. And again, UT is the altitude. And we know that the altitude is the geometric mean of both parts of the hypotenuse. So I know that I'm going to be setting up a proportion where UT is across from itself. And now I'm going to fill in the parts of the hypotenuse. Their position does not matter here. So let's say I've got SU on one part and UR on the second part. And here's why this works, by the way. If we take a look at these similar right triangles, I know that UT, let's color these in here for a minute. The smaller triangle is shaded in blue, and the second biggest triangle is shaded in red here. Okay. So I know that the ratio is going to reflect different legs and the hypotenuse of these triangles. So in the smaller triangle, we are looking at the ratio. So UT is the long leg. So the ratio of the long leg to the short leg, because that's UT over SU. And we are comparing it to the ratio of UR over UT. So UR in the red triangle is actually the long leg of that triangle. And UT, the altitude, is actually the short leg. If you rotate that in your head, UT is the short leg of that red triangle. So it all works out. You can remember it this way by the corresponding parts of the triangle, or you can just remember the altitude is the geometric mean of both parts of the hypotenuse in that big triangle. Lots of ways to think about the problem here. So in either case, I know that UT is unknown. So let's just call it X for the sake of it. And SU is 5.4. And UR is 9.6. And UT is unknown. So really, we are finding the geometric mean of 5.4 and 9.6. So multiplying across, we get x squared is equal to 51.84. And when I take the square root of that, I get x is equal to 7.2. So the altitude, UT, in this triangle is 7.2 units, using that property. So I've got another one. So the second corollary, the second follow-up to that theorem says the altitude from the right angle in a right triangle, so let's label it in green here, that's CD in this right triangle. So this altitude divides the hypotenuse so that the length of a leg, let's examine AC first. So leg 1 is going to be AC. This leg is the geometric mean of the whole hypotenuse. The whole hypotenuse in this triangle is AB. It's the geometric mean of the whole hypotenuse and the portion of the hypotenuse that is closest to that leg. So I'm trying to break up this theorem so it makes a little bit more sense. So the first part of this corollary says leg 1, one of the legs, is the geometric mean, meaning multiply across. It's the geometric mean of the whole hypotenuse and the portion of the hypotenuse, H1, that is closest to that leg. We can also apply the same to the other leg in this triangle. So CB is my second leg. Let's just call it leg 2. I'll label in a different color. So leg 2 is the geometric mean of the whole hypotenuse and the portion of the hypotenuse that is next to it or adjacent to it. So that would look like this. Leg 2 is the geometric mean of the whole hypotenuse and the portion of the hypotenuse that is closest to it. You could also examine this by breaking up the triangles into 3 separate triangles and noticing the proportions created by those side lengths. So let's try this out using triangle JKL below here. We are asked what is JL and what is KL. So let's separate this out a little bit. So A, we are trying to find JL. And JL is the short leg in this bigger triangle. So let's just call it leg 1. I know that leg 1 is the geometric mean of the whole hypotenuse. So whole hypotenuse is JK, and the portion of the hypotenuse that is closest to that leg. So JM. So let's fill in what we know. Leg 1, we're just going to call JL. JK, the total length is 4 plus 20, so it's 24 units. And it's equal to the smaller portion of the hypotenuse, which is 4 over JL. So now we're going to solve as normal. Cross multiply. So JL squared is equal to 4 times 24, which is 96. And so when I take the square root of both sides, I get JL is approximately, let's say to the nearest tenth, 9.8. So I know JL is 9.8. So now I can use that same concept to find KL. So KL is going to be my other leg. And here is the portion of the hypotenuse that is next to it. So I know that KL is the geometric mean. Again, setting up cross multiplication here. KL is the geometric mean of the whole hypotenuse, 24, and the portion of the hypotenuse that is next to it, so it's 20 units. So as before, we're going to cross multiply as normal. KL squared is equal to 20 times 24, which is 480. Which means KL is the square root of 480, and that is approximately 21.9. So in this problem, JL is 9.8, KL is 21.9. A great way to verify problems like this, if you have all of the missing sides in a right triangle, is to use the Pythagorean theorem. Make sure that you solve things correctly. If the Pythagorean theorem says a squared plus b squared does not equal c squared, then you're going to have to go back and try and reevaluate what went wrong. All right, last but not least, I've got a problem with a bunch of parts to it. I'm given this right triangle and it is divided along the altitude of the right angle, and I am asked to find the values of x, y, and z. I'm going to preemptively divide up my page a little bit here. And I think I want to tackle finding x first. So to find x, I know that the places where I see x are in the hypotenuse of my bigger right triangle. So let's call this hypotenuse part 1 and hypotenuse part 2. So I know that with the first corollary, I know that the altitude of a right triangle is the geometric mean of each portion of the hypotenuse of the right triangle. So the altitude is the geometric mean of both parts of the hypotenuse. So H1 and H2. And so I'm going to fill in what I know. So the altitude in this problem is 6. Hypotenuse 1 is x plus 5. And hypotenuse 2 is x. And the altitude again is 6. So now I need to cross multiply. So I get x times x plus 5 is equal to 6 times 6, which is 36. I'm going to distribute the x. And so I'm going to get x squared plus 5x is equal to 36. And so I'm actually I'm noticing that I have a quadratic equation in the making here. So I'm going to move the 36 to the left side of the equation. So let's continue this up here. So my quadratic equation looks like this. X squared plus 5x minus 36 is equal to 0. So you could either use the quadratic formula here. Remember, this is A, B, and C in your quadratic formula. Or you can use the sum product method for factoring this equation. So I'm asking myself, what two numbers add to be positive 5 and multiply to be negative 36? And just to keep things brief here, I know that the numbers that add to be positive 5 and multiply to be negative 36 are negative 4 and positive 9. So when I factor this quadratic equation, I get x minus 4 times x plus 9 is equal to 0. So now to solve this equation, I've got two mini equations. X minus 4 equals 0, and I have x plus 9 equals 0. And so the result of these equations, I get x equals 4, and I get x equals negative 9. Now, negative 9 cannot be a side length, so that I'm going to use the positive solution, x equals 4. So to help us out a little bit here, and to fill in the information we know, we're going to need to use the parts of the hypotenuse to help us solve for y and z. So I know that hypotenuse part 1, h1, is 4 plus 5, so it's 9. And I know that the other part of the hypotenuse is x, so it's 4. Let's label hypotenuse 2 in a different color here. Okay, to find y. To find y, let's move up to the top. I know that y is a leg of the triangle. So I'm going to use the proportion that tells me, let's call this leg 1, or let's call it leg 2. So I know that this leg is the geometric mean of the whole hypotenuse and the portion of the hypotenuse closest to that leg. So let's fill in what we know. Leg 2 is y. And the whole hypotenuse is just 9 plus 4. So that's 13. And it's equal to the smaller portion of the hypotenuse next to the leg, which is 4 units. And leg 2 again is y. So we're going to cross multiply. Y squared is equal to 13 times 4, which is 52. And so when I take the square root of 52, I get y is approximately, let's say to the nearest tenth, 7.2. So I have x, I have y, now I need to find z. So z is another leg. Let's call it leg 1 because it corresponds to H1, that portion of the hypotenuse. And I know that this leg is the geometric mean of the entire hypotenuse and the portion of the hypotenuse next to the leg. So let's fill in that information. Leg 1 is just z. The whole hypotenuse is 13. The portion of the hypotenuse next to z is 9. And of course, leg 1 is z. So again, cross multiplying, z squared is equal to 9 times 13, which is 117. And so z is the square root of that. So z is approximately 10.8 units. So we successfully used geometric means and the altitude of a right triangle to find these missing side lengths. And again, to verify the lengths of these side lengths, I strongly recommend using the Pythagorean theorem. Test out if the sum of the squares of the legs in your triangles is equal to the square of the hypotenuse of those triangles. So that is our lesson. There's a lot of information in here. So a quick summary. The two corollaries of this lesson say that the altitude of a right triangle is the geometric mean of each part of the hypotenuse. Each leg of a right triangle is the geometric mean of the whole hypotenuse and the portion of the hypotenuse it is next to. And we know that the altitude in any right triangle creates 3 similar right triangles. And when you're solving problems involving the geometric mean, it is going to be extremely helpful to you to draw and label each right triangle separately in order to write a proportions. You can set up proportions with, let's say, the short leg to the hypotenuse is equal to the short leg of another triangle to the hypotenuse of that triangle. Let me know if you need any help. Thanks for watching and take care.